for inviting me, and also thank you to the organizers for setting up this fantastic conference. Okay, so I'm going to be talking about stops, but before I directly get to stops, let me kind of give an example that kind of will show the type of thing that I want to explain. So we start with, say, P2. So let me just draw. Is this too small? No, it's fine. Draw. Here's P2, and that's going to be mirror, as we know, to well, it's mirrored. We can either say to W y plus 1 over xy, or we can also draw this in this way. And we're going to stick a bunch of hair at the origin, and then just a little bit of hair on each of these other things.
I mean, lateral support or something.
Yeah, I just want to draw some pictures right now. I don't want to kind of say anything too detailed, because this is just kind of the very basic motivation. And then I can look at P2 minus 3 points, and I lose W. So let's draw this. Kind of just draw these points missing. And, well, W is gone, but we still have this picture. And this was studied by Kitsarkov and Kerr, or a related example.
Actually, I remember.
Yeah.
Yeah.
Yeah. That you were originally involved in?
Yeah.
So there's no more W, but we still have this FLTZ type picture where now we've just removed all of the hair around the origin.
And no diagonal.
Oh, sorry, yeah, there's a diagonal. Sorry. Okay. And a thing that happens, so over here, we have a theory that this is Lefschetz vibration, and the structure functors on the A model associated to a Lefschetz vibration are spherical. Here, the push forward along this divisor, the toric divisor, is still spherical, but we can't explain that anymore using a Lefschetz vibration. We need some other explanation, symplectically, for why the structured functors associated to the skeleton are spherical. So that's what I'm going to explain today. So it's worth saying that almost nothing I say is going to be new. I think there's going to be one symplectic lemma, and everything else is in the convex hull of what's been said already at this conference. But it's a nice picture. So hopefully it'll be worth it. Okay. So one. Let me start with some definitions. Definition. And this, well, I'll begin by repeating things that Sheil said. Legal domain. It's going to be lambda is a manifold. This is dimension 2n with boundary such that d lambda is symplectic, and the Liouville vector field the vector field associated to this one form points out along the boundary. Okay, so we'll give the standard examples. And these are essentially all the examples that we're really going to care about, at least for these purposes. For example, some affine variety, or equals T star Q for some smooth manifold Q. Okay. So now we can define the stop in M is a Liouville hypersurface. No, is it hypersurface? Sigma in the boundary of M, with boundary, not empty boundary, such that sigma with the one form restricted to sigma is a Liouville domain, which I'm just going to read the LD. Okay. And just like with Liouville domains, there are two standard examples of stops. So if we have a W from M to C, some potential, then we can define sigma is, well, it's some projection. I'm going to suppress the projection. It's going to be W inverse of, say, plus infinity. Be the generic vector projected to the boundary. Another example, if we have lambda in the boundary of M Legendre, then we have sigma is, well, modeled off the cotangent bundle of lambda, sitting inside the one-jet bundle of lambda, sitting inside boundary of M. So the contact neighborhood of one-jet bundle of lambda. So the contact neighborhood theorem says that any smooth Legendrian has a standard neighborhood which looks like some tube around the zero section in the one-jet bundle. I'm suppressing the tube. And I'm taking the kind of cotangent part of that.
And this should be generalized to singular Legendrian.
This should be generalized to singular Legendrians, but we don't have a good procedure to say when we can produce such a thickening. Singular. I'm going to say very tame. And we get a similar situation. I'm not going to say what very tame means. Probably arboreal is, well, almost certainly arboreal is fine, probably some other cases. So when I have a Liouville domain with a stop, I'm just going to call that a sector. There are technical definitions which are kind of a little bit more convenient for setting up Floer theory, but essentially a sector is a pair. Well, I guess it's a triple. No. Pair of some Liouville domain M and some stop sigma. associated to any sector. We have a Fukaya category. Which I'll just write W of M sigma. And this is equipped with some extra structure that keeps track of the stop. And so that extra structure is a functor this is due to Orlov. And it's usually called cap functor. I'm going to write I sigma, and it goes from W of sigma to W of M sigma. So let's draw a picture of this. So I'm going to draw a picture as if sigma were the fiber of some superpotential. It turns out any stop is locally of that form. So here's M, here's the boundary of M, and here's sigma. Again, as if sigma were the fiber of a superpotential. So in this picture, there is a canonical curve. Maybe I need it. There is some curve gamma. And I sigma of some Lagrangian in the fiber is just its product with this curve gamma.
Canonical means it doesn't depend on the choice of sigma.
Up to homotopy. It's kind of, so up to a contractible set of choices, there's a unique projection to C, and you can just write down what this gamma is. Well, this is the structure we have. This is the Floer theory associated to a leavable sector. Okay, so what can we do with this? Well, given any stop, there are two kind of natural operations. So I'm again going to draw this picture. Leave up the labels with the same picture as before. So one thing I can do is I can delete it, and then I'm left with no stop. So I've replaced this data with no data. Or I can double it. And then nope, I failed to double it.
Triple.
What's that?
Or triple, yeah.
Yeah, I can also triple it, but
yeah,
tripling is like iteratively doubling.
Yeah.
And then there's some kind of isomorphism.
0 and 2.
Yeah. Turning it into 0 and turning it into 2 generates all the other things you can turn it into.
Okay.
But the nice thing is that kind of these come with particularly simple descriptions at the level of Fukaya categories. two versions, essentially. And this is called stop removal. So it says, if sigma is nice, and well, the difference between these two versions is exactly what we mean by nice, but any sigma of the form described up there is nice. Then the Raphukai category of M is equivalent to the partially Raphukai category W M sigma modulo the objects in the image of sigma, or in the image of I sigma. So if we understand this partially Raphukai category and we understand I sigma, then we understand the resulting category of the ambient viewable domain. B is maybe a little bit more interesting. And I guess it's worth saying that kind of all of these have analogs at the level of Schober's, and from that perspective, I'm not saying kind of anything surprising. So let's draw some pictures first. Sigma here. And so now I'm actually going to replace sigma with two things, with a sigma plus and a sigma minus. I'm going to forget about sigma shortly. So in that sense, I'm really just doubling rather than. And so let's draw some curves. So now I'm going to call, here's gamma. Here's gamma plus. And here's gamma minus. So, kind of, as a geometric corollary to the stop removal, W of sigma plus union sigma minus is equivalent to some gluing of categories, equivalent to W of this one, W of sigma, glue on I sigma in that direction to W of M sigma. Now this is often just written, this is essential, this is the same thing as what's often just written semi-orthogonal decomposition W of sigma, W of M sigma. I'm just keeping track of what the gluing data is. So this specifies a category rather than just needing to know the category ahead of time. Okay. And in this description, we can understand these new inclusion functors. So, I should say under this equivalence, we have I guess split this up. I sigma plus is the identity from W of sigma to W of sigma, and I sigma minus. So again, I sigma plus is take a Lagrangian in sigma, think of it as a Lagrangian in sigma plus and cross it with gamma plus. I sigma minus is the same thing for minus. This is a cone of identity with the shift. I think it's a shift by 1. I know it's a shift by 1 to I sigma. So given sigma, given sigma, we duplicate and we understand the new category. We already know what the Fukaya categories of the fibers are, and we know what the inclusion functors are. So we've recovered all of the information.
It's kind of completely obvious from this point of view, skeletal, just skeletal edges.
Yeah.
Fork, it's
Yeah.
A to Fuga.
I agree.
Yeah.
I guess what should I say? So this is an instance of the Cauchy property.
Yeah.
Though I don't know of any proof in the literature that kind of says that this gluing is the appropriate colimit. I think it's pretty clear that it is. But, missing. All right, that's the setup. On 2, we're going to talk about swaps. Oh, I should say geometric swaps. So we start with the lemma. So sigma plus sigma might be a doubled stop. So I'm going to write various things you could ask about this. There's a space shortage. Well, let's say A implies B, implies C, implies D, where there are various properties I could ask of this. So A, I can ask, there is a simplexomorphism of exchanging. I guess I should really say the completion of M. Of M hat exchanging sigma plus and sigma minus. B, I'm going to run out of space. Anyway, there is a contactomorphism of the boundary of M exchanging sigma plus and sigma minus. So far, completely obvious. Restrict to the boundary. Can't go any higher. Okay. Let's continue the lemma over here. C. Sigma plus is positively isotopic to sigma minus in the complement of sigma. D, sigma plus is isotopic to sigma minus in the complement. Further, so it should be obvious that A implies B.
Complement dm minus sigma.
Oh,
Yeah.
in
In dm, yeah.
the yeah.
Okay.
So, yeah. It should be obvious that what A implies B and that C implies D, and it's not difficult to see that B implies C, but I'll prove that to you in a minute. But let's say furthermore. If the isotropy in D restricts to an isotropy of very tame skeleton, then D implies A. So let's see. Let's give the proof of this. And very tame there might be even more tame than over there. But it's certainly true for smooth skeleta. It's certainly true for skeleta with conical singularities. It's probably true for arboreal skeleta, but I haven't fully checked.
Is it true for skeleton of Weinstein hypersurface?
I don't know. I guess I should also say, after a small global perturbation. Global here means I uniformly perturb sigma plus and sigma minus, rather than just perturbing one or the other. I perturb sigma plus and sigma minus in the same way, and then this becomes true. The proof. So let's start with B implies C. So I have, let's draw it this way. We have sigma, we have sigma plus, we have sigma minus. So now I have some contactomorphism which sends sigma plus to sigma minus and vice versa. So let's apply that contactomorphism. Let's grab another color. I guess it's just green. Let's apply that contactomorphism to this short positive path. I'm going to get some new some new positive path, not necessarily short. So this is contactomorphism too short. Short positive path. And this new thing could well intersect sigma. It could intersect the original. No, sorry. What do I say? Well, maybe it actually just can't intersect sigma. Okay. I guess actually there's nothing to say. Okay. Okay, you take this short positive path, you apply the contactomorphism, and now you get a
Some positive path from sigma plus to sigma minus. Yeah.
you get a positive path from sigma plus to sigma minus.
But it's on the complement of sigma.
And so I'm trying to decide if it's obvious that it's in the complement of sigma or not. But let's say it's not obvious.
Yeah.
I thought it wasn't obvious, and suddenly I had some hallucination that told me that it is.
I think it's obvious, yeah, because you have just
It's a
domain.
contactomorphism.
You have a
apply it-
domain which looks outside, and yeah.
Wait, no, I mean, this. I never said anything about this contactomorphism kind of not having fixed points, or anything like that. Okay, so it's not obvious that this is in the complement of sigma. In fact, this could well cross sigma. However, it's an embedded path. Its image is an embedded path, and it's positive at the endpoints, which means it's embedded in this region. Let's call this region U. The concatenated path loop is embedded in U, which is some neighborhood of sigma plus. So now I'm going to replace sigma by sigma plus by some sigma plus plus and sigma minus by sigma plus minus. So I can just zoom in there, which is equivalent to what I started with. So now this is some global or some positive isotopy sigma plus plus.
Again, I think if you replace the sigmas, which are really very high dimensional, by the skeleton, it will be more obvious. Yeah, like Lagrangian things moving.
Yeah.
Yeah.
Yeah. So that's
Yeah.
yeah. I agree. But kind of the Lagrangian things, they can still intersect. The
Yeah.
original thing can still intersect sigma. It's essential to zoom in
Yeah.
so that you can get this path in the complement.
Yeah.
That's the proof. Oh, that's the proof of B implies C. Maybe I'll just say the proof that D implies A. There's an isotopy extension lemma for isotopies of Legendrian submanifolds, and you apply that. So you have some isotopy, and you convert that into a contactomorphism. While you're isotoping sigma plus to sigma minus, you'll just isotope sigma minus up to sigma plus. Any questions on the lemma?
So can you tell in the picture what's the positive direction? Is that
Positive direction is
Minus to plus.
plus, yeah.
Okay.
Minus to plus. This is the end of the new part of my talk.
Okay.
The beginning and end. Okay. So why should we care about this stuff?
Sorry, another question. Is it possible to formulate as to have an S1 vibration of sigma with fibers anthropomorphic to sigma? And you have
No,
contact
because
that
this path can cross itself.
Yeah.
So that was the S1
but this
vibration.
thing happens for Landau-Ginzburg models. Yeah.
Yes, exactly.
Yeah.
So for Landau-Ginzburg models, you have an actual S1 vibration. And in fact, for the motivating example, you still have an S1 vibration where you take as your stop these one-sided conormals. So if there's time, I'll draw that, but I want to make sure I can say something about spherical functors as well, even if it's already been said. Okay, definition. Sigma is swappable if, I should say, G holds. Okay. The other criteria say that you can check swappability in a fairly straightforward way. So let me just say that the Criterion C has already appeared in the literature. Let me state a theorem that was proven assuming Criterion C. I should. Theorem of symplectic topology. If the cosphere bundle of P, and P as a manifold Q, is swappable in P star Q, then two things are true. First, H star of the universal cover of Q with C coefficients is a truncated polynomial ring.
So P is a point, yeah, consider.
P is a point. P is a point in a smooth manifold. So this is a generalization. It's a symplectic version of the Bott-Samuelson theorem, which I won't state. It says the same thing where you replace like positive isotopies with geodesics. So that is a truncated polynomial ring. And secondly, that pi 1 of Q has order at most 2. So those follow from swappability of this coaster. They didn't use the language of swappability. They were considering condition C, but they're all the same. Okay. Anything else about this? All right. 3. So let me go and stare at this lemma and kind of say, there's an algebraic version of condition A. The definition spherical swap of a functor F A to B is an autoequivalence of this category. A includes along F to B, exchanging F plus and F minus, where F plus and F minus are defined algebraically like that. Okay. Is it visible at the top?
Exchanging, you see that also F up to action of automorphism of B, yeah? Because you get
Yes, absolutely.
yeah. Not literally map to B, but map to.
Oh yes, let's actually correct that. automorphism of A.
Of A, B as well? Because you get your
It's an
sequence also-
autoequivalent of this thing, and
B was
kind of.
B was your boundary,
No,
integer?
no. So A is the source. So A is the stop.
It's a stop. Homotrophies of A here.
Two. Equivalently, you can just say exchanging the images of f plus and f minus.
Yeah. So it really fits with very well this first talk this morning here, which was exactly this symmetries here. Subcategories here.
So let me then go and recall. Actually, well, I shouldn't. I don't want to spend the time writing the definition of a spherical functor. Recall that a spherical functor is defined by certain cones being autoequivalences, and if I have time to use the criterion of being spherical, then I'll write down the cone that I care about. But let me recall. Theorem that Misha stated. A functor f is spherical if and only if this gluing, if this gluing extends to a 4-periodic semi-orthogonal decomposition. Which it's worth saying. So the convenient thing is in this picture, without assuming any adjoints of f, so f, we don't assume admissibility, the inclusion of B has left and right adjoints. Therefore the inclusion of B into this is nicer to talk about semi-orthogonals. So I'm just going to say i.e. B with 4 orthogonals equals B. Okay. So the corollary f is spherical if and only if f admits a spherical swap. It's easy to see if f admits a spherical swap, then this must be the case. And if you look at the proof of this theorem, you will see that Helper, Leitzner, and Shipman construct a spherical swap as part of proving this. So I guess I should write the corollary to that. If sigma is swappable, well, we know that that isotopies of the stop induce equivalences of the Fukaya category, and so if sigma is swappable, then I sigma is swappable, or no, is spherical. So what this does is this gives a geometric picture of why these functors, why the structure functors for these skeletal mirrors that don't come from Landau-Ginzburg models still are spherical. I'll try to stop a little bit early, but before I do, let me just say, why do I care about this as a symplectic geometer? Okay, so you recall a theorem that Tobias stated, Ekholm Zakili, both of whom are no longer here. But in any case.
They're ghosts.
What's that?
The ghosts.
The ghosts. So their theorem says that, so let lambda in the boundary of M be Legendre. So let L in T star, let L T P star lambda in T star lambda a cotangent fiber. Then the Legendrian DGA, which they're writing the Chekhov Elyasberg, of lambda with these non-central coefficients in the base loop space is equivalent to hum in, well, let's just say end in W of M, I'm just going to say W of M lambda as, I think of lambda as the stop of I guess I should, I'll say M sigma. So sigma is the stop associated to lambda. I sigma L. I sigma L. They prove this, and they prove it in a way where if you unwrap this and do a bunch of extra work, it's compatible with the action of chains on the loop space. That compatibility is not in the paper, but and if the maps are defined the same way. So at least up to a twist, you're going to get some compatibility. Okay. So now, well, suppose lambda is swappable. Then this functor I sigma is spherical, and so we can start rewriting this. Then CE is equivalent to, well, I can take, say, the right adjoint, and do a larger chunk, in W of T star lambda of L with right adjoint I sigma L. Right? And now this thing is equivalent using one of the exact triangles in the definition of a spherical functor. Let's see which one. R cone of some monodromy applied to L to identity to L. This is and this monodromy is really the equivalence of the Fukaya category of the cotension bundle induced by the geometric monodromy of the swap. It's not just anything. Oh wait, sorry, it's the inverse of that. I'll just say M inverse. The inverse of the geometric monodromy. Okay. But now the geometric monodromy sends L to L. So this thing is some cone of end L to end L, which is cone of, in other words, chains on the loop space of L to chains on the loop space of L. And I'm omitting a shift. There's some shift, which I don't have written down. So, in other words, it tells you that the Chekhov-Ashberg DGA is generated as a module over chains on the loop space by 2 copies of chains on the loop space. So it's very small. At least you can strongly control what it could possibly be. I'll stop there. Thank you.
Can you use this kind of things to kind of distinguish something like swappable or not?
Yeah, so this is a pretty easy abstraction to something being swappable. I mean, this tells you that swappable Legendrians are very rare.
So there are many counterexamples
Yes.
of this.
Yeah. There are very few examples, in fact.
Yeah. Nice.
But this makes it easy to see that there are few examples.
Okay, thank you.